Hello friends, myself Pramod Musrif from AISSMS Institute of Information Technology, Assistant Professor in Engineering Physics. Today we will see about the P-type and N-type semiconductors. The topics covered in the today's session are the semiconductors, electrons and holes in semiconductors, intrinsic semiconductors and extrinsic semiconductors, and then P-type semiconductors and N-type semiconductors. Basically, semiconductors have the resistivity between the good conductors and insulators. The resistivity of semiconductors lies approximately in between 10 to the power minus 2 ohm meter and 10 to the power plus 4 ohm meter at room temperature. If you plot a graph between temperature versus resistivity or resistance of the semiconducting material, it is observed that the resistance decreases with the temperature for the semiconductors, whereas it is contradictory to the metallic conductors. For the metallic conductors, the resistance increases with the increase in temperature. If we plot a graph between the temperature and the resistance increases with the temperature. The best examples of the semiconductors or pure semiconductors are silicon and germanium, commonly used semiconductors. We will go for the electrons and holes in semiconductors. As all of you know, the semiconducting means the energy levels in solids are in the form of bands, and the valence band and conduction band is there. So at zero temperature, in pure semiconductor, valence band is completely filled and conduction band is empty. But if you increase the temperature, what will happen? The electrons in valence band will absorb the energy and they will go to the conduction band. Valence band is the lower energy level and conduction band is higher energy. Now if you go for silicons, it has 4 electrons in its outermost shell. So this is a lattice structure of the silicon. Now if you supply energy, means if you increase the temperature, some of the electrons from valence band, they go to conduction band, creating holes in the valence band. So white dots are the holes in valence band, whereas these are the black dots are the electrons. So one of the electron from valence band has gone to the conduction band, generating hole in valence band. So in this way, the electrons and holes in semiconductors are. So holes are, these are not as such particles, but it is a deficiency of electrons. Holes are nothing but it is a deficiency of electrons. Now, if you go for the lattice structure at high temperature, what will happen? Few of the electrons, they will be going to the conduction. So these electrons are the free electrons and they are generating the holes here. These are the holes created because of the applying the energy, or if you supply energy to these silicon atoms. The electrons in an intrinsic semiconductor which move to the conduction band are called as intrinsic carriers. The vacancy created in the valence band is called as holes. The importance of holes is that it may serve as a carrier of electricity in the same manner as that of the free electron, but the motion is opposite in direction. So in this way, if you see here, the electron is moving from one place to another place and generating the hole at another place. So in this way, electron is moving and hole is moving in opposite direction to the direction of motion of electron. If you go for the periodic table, there are group 3 elements, group 4 elements, group 5 elements. Silicon, germanium are group 4 elements. So in their outermost level 4 electrons are there. Now group 5 elements have more electron in their outer shell. You go for phosphorus, arsenic, they have 5 electrons in their outermost. So like all atoms, they have same number of protons in it. This extra electron, which is a negatively charged, is not tightly bound to the crystal lattice of the silicon atom and can be easily separated from its parent atom with addition of only a lattice. Thermal energy at room temperature is easily enough to do this, meaning that electron is essentially free to move from the moment of the phosphorus atom is introduced into the silicon crystal. So if you add these fifth group elements in the silicon or germanium, then this 4 germanium atom, 4 phosphorus atoms will be bound with the silicon and one atom of the phosphorus will be free, and this will be, in this way the free electrons will be generated, and in this way we can have this extra electron by adding the phosphorus atoms in silicon crystal. So this is called as N-type semiconducting material because you are getting the one extra electron in this case. In the same manner, if you add group 3 element which has 3 electrons in outermost level and valence extra, so there is an extra hole, and this extra hole will be acting as a charge carrier. In this way, the hole can move through the crystal lattice. Although hole carriers have no charge, but the electrons which are moving into the represent a negative charge moving in opposite direction to the hole. Therefore, we think hole is moving as a positive charge. So, this B atom is having 3 electrons. So it is bound with the 4 silicon atoms. So one deficiency of electron is there, which is known as the hole. So in this way, this p-type material and semiconducting material and n-type semiconducting material are classified by adding the doping of the third group element and fifth group